Hello and welcome to this GCSE Chemistry video about electrolysis of aqueous solutions. We're going to start by looking at what makes aqueous solutions different to molten electrolytes, then focus in on what happens at the electrodes, and finish by exploring how we can predict the product of electrolysis of aqueous solutions. Electrolysis is a process where electrical energy is used to make a chemical reaction happen. In electrolysis, you need to have some kind of container, possibly a beaker, with an electrolyte in it. The electrolyte needs to be an ionic compound, and the ions in that compound need to be free to move. And so this means that we could have a molten ionic compound. That's necessary if the electrolyte is insoluble. Or we could have a solution that we could use for something that was a soluble ionic compound. But both of these have got ions that are free to move. In this video, we'll take a look at what happens when you use aqueous solutions, which are more complicated than using molten electrolytes. To make the electrolysis work, you need to put two electrodes into your electrolyte. These need to be made of some kind of inert substance, which means that they are unreactive and so won't react with the electrolyte. We normally use graphite, which is a form of carbon, or platinum. We need some kind of power supply to drive this electric current, and it needs to be a direct current because this ensures that the electrons move in one direction and build up on one of the electrodes. And the electrode that they build up on is the negative electrode, and this is called the cathode. And the electrode where the electrons came from is the positive electrode, and this is the anode. And since opposite charges attract, the positive and negative ions move towards their oppositely charged electrode. And so that means that the negative ions move towards the positive electrode and the positive ions move towards the negative electrode. And both of these types of ion become discharged when they reach their electrode, and that turns them into the element that the ion was made from. An aqueous solution is formed when a solute dissolves in water. In electrolysis, the solute needs to be a soluble ionic compound, for instance, sodium chloride solution, which we might write NaCl with the AQ state symbol after it, which means that it is aqueous. In a solid form, sodium chloride exists as a three-dimensional ionic lattice containing positive sodium and negative chloride ions. But once this substance has dissolved in water, we have got separated sodium 1+ ions and negative chloride 1- ions. And once the ionic compound has dissolved in water, these ions are free to move. In an aqueous solution, the water molecules themselves break down, and this produces hydrogen ions, H+, and hydroxide ions, OH-. And I'm showing an equation for this breakdown inside the beaker itself. When you carry out electrolysis on an aqueous solution by putting in your electrodes connected to leads and your DC power supply, this creates an issue, since there are two positive ions, both attracted to the negative electrode, and also two negative ions, both attracted to the positive electrode. But only one of each type of ion gets discharged. And so that raises a really important question. Which ion gets discharged at each electrode? In theory, both of the positive ions will be attracted to the negative electrode during electrolysis, but only one will get discharged, that means lose its charge, while the other will stay in solution. In general, the ions discharged when an aqueous solution is electrolyzed will depend on the relative reactivity of the elements involved. So at the negative electrode, the cathode, we are deciding between a metal ion and the hydrogen ion from the water. And the rule for deciding which will be discharged is this. If the metal is more reactive than hydrogen, the hydrogen ion will be discharged and hydrogen is produced. if the metal is less reactive than hydrogen, then the metal will be produced because the metal ion is discharged. I get asked a lot why it's the more reactive ion that stays in solution, rather than it going to the electrode because it's more reactive. The best way of thinking about it is this: the more reactive an element is, the more readily it reacted to become an ion, and so the more likely it is to stay as an ion. And so to resolve this problem, we need to use the reactivity series, which shows how reactive each of these metals is and compares it to hydrogen, which is included for just this comparison purpose. And you can see that in fact most of the metals are more reactive than hydrogen, but there are a few that are less reactive than hydrogen. And so if we take some examples to practice this, if we first look at potassium bromide solution, which contains the potassium ion and the hydrogen ion, we find potassium at the very top of the reactivity series, and so it is more reactive than hydrogen. And so the hydrogen will be the ion that is discharged, and so hydrogen will be produced at the negative electrode, and we will see bubbles of gas. We wouldn't know that it was hydrogen without testing it, but we would definitely see the bubbling. In a second example of copper sulfate solution, which has got copper 2+ ions, we can compare the reactivity of hydrogen and copper, and we find that copper is less reactive than hydrogen. And so that means that the copper ions will be discharged, and we'll see a buildup of copper on the negative electrode, or perhaps it would fall off and build up underneath the electrode. To make things faster for yourself, it's probably better to check for the metals by name that are less reactive than hydrogen, because there are so few of them. And in fact, gold is very unlikely to be used as an example because there are so few solutions that involve gold. And really silver is probably unlikely. So really the metal to watch out for is copper. Most of the others are more reactive than hydrogen. Working out which ion gets discharged at the positive electrode during the electrolysis of aqueous solutions is probably the easier of the two, because what we're doing on this occasion is we're looking for the presence of an ion from a particular group of the periodic table. And so whilst reactivity is still a factor, we don't really need to consider it. The most practical approach is to look to see if the solution contains a halide ion. And the halide ions are ions formed when the group 7 elements gain an electron to fill their outer shell. So really we're looking down group 7 to see if there is a halide ion present. And so this would be fluoride, chloride, bromide, or iodide. And if there is a halide ion present, we produce the halogen that corresponds to. So fluorine, chlorine, bromine, or iodine, remembering that all of the halogens are diatomic molecules. If there isn't a halide ion present, we produce oxygen gas, and this oxygen gas comes from the hydroxide ion. And so if we consider the same examples as before, first potassium bromide, we have got the two ions, bromide and hydroxide. And so we look down group 7 of the periodic table and we find that we've got the element bromine in the bromide ion. And so that means that the bromide will be the ion attracted to the positive electrode. And when it gets there, it will get discharged and produce the element bromine. And we might well expect to see the production of a gas at this electrode. In a second example, if we had copper sulfate solution, we would expect to have the hydroxide ion, again from the water, but also this time sulfate. When we look down the group 7 this time, we see that we haven't got any group 7 elements, so that means there is no halide ion to get discharged, and so we won't get a halogen. Instead, what will happen is the hydroxide ion will be the ion attracted to the positive electrode, where it will get discharged and produce the element oxygen. And so oxygen gas will be produced, and we will observe bubbling. and we won't know that it's oxygen gas without further testing, but we'll definitely see the bubbling. If we carry out electrolysis on an aqueous solution of sodium chloride, NaCl, we get 3 useful products, and we can work out what those products will be by using the rules for electrolysis of aqueous solutions. First of all, looking at the ions that there are present, we've got the positive sodium ion and the negative chloride ion from the ionic compound. And from the water, we have the hydrogen ion and the hydroxide ion. If we first consider the negative ions being drawn towards the positive electrode, we've got the hydroxide ion and the chloride ion. The chloride ion is a halide ion, and so that means that this is the ion that is attracted to the positive electrode and then gets discharged, and we make the element chlorine as a product at this electrode, and we would observe bubbling. And chlorine is a useful substance that can be used to kill bacteria. When it comes to the negative electrode, we have got the sodium ion and the hydrogen ion. Sodium is more reactive than hydrogen, so it will be the hydrogen ion that gets attracted towards the negative electrode and is discharged. And we will make the element hydrogen and we will observe bubbling. Hydrogen is a really useful product used as a fuel. And then the ions that are not discharged at the electrodes remain in the solution, in the electrolyte. And in this case, it was the sodium ion that didn't move to the negative electrode and the hydroxide that didn't move to the positive. And so the substance in the electrolyte is sodium hydroxide, which we can use to make bleach and other cleaning products. Okay, that's the end of this video. Thanks for listening.